Right, so I want to look at the idea of an infinite geometric sequence and the scenarios in which you can find the sum of a sequence in which the terms go on forever. And so for these questions, I want to find that sum if it is convergent, which means it's possible. So if it's convergent, that means every subsequent term gets closer to zero. And that is not the case in this sequence. And I can always tell by finding the common ratio, which recall, common ratio is, you can always find by taking any term and dividing by the term before it. So in this case, 5/2 divided by 2. Which, however you approach this, is 1 1/4, 1.25. So this is not convergent, which means every subsequent value gets larger or gets farther away from zero. And so if you do that forever, you just keep getting larger. You just keep finding the sum of values farther and farther away from zero. They don't come to us a finite number. And so we just say not convergent, which means we can't actually find the sum of all these terms should we go on forever. But we'll see something different here. Now, in this case, if I find the value of the common ratio, pick a term, divide by the one before it. In this case, I get 3/2 divided by -2. And if we simplify this, we get -3/4, which, because the absolute value of the common ratio is less than 1, that means this is convergent. Which means with each subsequent term, the values get closer and closer to zero, which means should we add these up forever, we can actually get a finite sum. And so in this case, that sum is the same as the first term, -2, divided by 1 minus the common ratio, which in this case is -3/4, not -34, -3/4. And so, being wary and careful of that double negative there, I get -2 over 1 plus 3/4, which is 7/4. Which I want to leave my answer as a fraction here because a decimal will be quite nasty. Please keep in mind the same as -2 times 4/7, dividing by any value, same as multiplying by the reciprocal. And I can see it exactly -8/7. So that's my infinite sum. Should I add all these values up forever? I would eventually, I would approach -8/7. We say approach because really you can't actually add up terms forever. But as you go on and on and on, the value gets closer and closer and closer to -8/7 forever. All right, so for this last one, first let's find the common ratio. To pick any term, divide by the one before it. And so in this case, I get √2 over 2√3 divided by 1/2. So in this case, multiply by 2 over 1. I'm going to just stick with fractions here to keep everything exact. My 2's cancel out, and so I can see my common ratio is √2 over √3, or √2 over 3. Either way, √2 over √3 or √2 over 3 is less than 1, and so this is convergent. And so I can find that sum using that same formula as before. The sum of the infinitely many terms is the first term, 1/2 divided by 1 minus the common ratio, √2 over √3. Now, I want to keep my value exact, which means as soon as I go to a calculator and I start decimalizing things, I'm no longer exact, so I'm going to avoid doing that. But I want to find a common denominator for my denominator first to clean this up. So I'm going to make this √3 and therefore make this √3. So I get 1/2 divided by √3 minus √2 all over √3. So keep in mind all of this became this. Similar, I got working through division with fractions. I'm going to think about multiplication with the reciprocal. And so in the end, my sum is √3 over 2 times √3 minus √2. There's my exact value. Keep in mind, if I were to decimalize it at any point, I'd get an approximation. I just didn't want to get an approximation. And since we are at an HL level, we need to be, confident and proficient with this sort of numeric and algebraic work. Okay, so for this question, I give us a couple facts about a geometric sequence. The sum of the first three terms is not the most pleasant number, negative 26.4063. So the sum of the first three terms, which keep in mind the sum of any geometric sequence we can figure out by going the first term times 1 minus r to the power of the number of terms, or in this case, the power of 3, divided by 1 minus r. That's just using our formula we've seen a long time ago for how to find the sum of a geometric series. And I know this equals negative 26.4063, so maybe I'll just substitute that in right now to save a bit of time. All right, I also know that the sum to infinity, should I add all these terms forever, which means this must be a convergent series, is exactly negative 80. So again, that infinite sum is the same as the first term, divided by 1 minus a common ratio. Well, I don't know the first term of the common ratio, but I do know all this comes to negative 80. And now what I notice here is I have two equations, each with two unknowns. And I can solve this in many different ways, but I do have a system here. And there's various algebraic approaches, although in general, if you have a system, it's perhaps you may quite prefer solving it by graphing or algebraically. I'm going to solve this by graphing. For example, I can quite easily isolate this first term in each of my equations. For example, with my infinite sum, if I multiply both sides by 1 minus r, I get my first term must be the same as negative 80 times 1 minus r. And if I do something similar for the other equation here, if I multiply both sides by 1 minus r and then divide by 1 minus r cubed, I get my first term must be the same as 1 minus r times negative, actually I'll put the negative 26 and change first, negative 26.4063 times 1 minus r, all divided by 1 minus r cubed. And I'm going to choose to solve this by graphing just because at this point, each of these equations I can type in relatively easily. I'm going to treat this is my y, I'm going to treat r as my x for each. Alternatively, I could solve this by a form of substitution. For example, if I just substitute all of that right here, I'll get two equations I could solve with algebraically, and a fair amount of things would cancel out nicely. It is all a matter of opinion. It should be fairly quick, and I can see that solving by graphing wouldn't be quick, so I'm going to solve by graphing. And when I do that, I get a solution at my x value is 0.875, and my y value is negative 10. Keep in mind, my x value in this case was my r, my y value was my u1, and so the question asks for the sum of the first three terms. Well, my first term I now know is negative 10, and so I can now, that's the most important, and my r value is 0.875. And so now I can find the sum of the first three terms by just, I'm trying to find the first term. Helps if I remember the question that I'm asking you to figure out. The first term, there it is right there. And I could really do anything else with these sequences now that I know the first term and the common ratio. All right, before I go on again, you could definitely solve that algebraically, and it's a matter of opinion if that would be faster or not. But solving by graphing should be pretty quick at this point. All right, here I have a fractal and a visual pattern here in which I say the area of each full triangle. So this whole region in here, all of this, I'm saying has an area of 1. So I want to find the area of all the shaded regions, just the shaded regions, but in all these figures should they go on forever. And so we can see a sort of visual pattern happening here, which means I can just see quickly in this first figure, the area, the shaded area is 3/4. 3/4 of a square unit, right? 1, 2, 3, 4 equal parts, 3 of them are shaded. For this second figure, what's the shaded area? Well, I can do something similar, especially if I just draw this. I can see eventually there are 16 equal triangles, and of those 16 triangles, 9 of them are shaded. Now at this point, I can already potentially find the common ratio. I can see to go from 3/4 to 9/16, I can actually just tell by looking at it, that must be, the common ratio must be 3/4. I could also take 9/16 and divide by 3/4 itself. So in this case, my first term and the common ratio are the same. How do I know, though, that this actually is a geometric sequence? Well, I don't tell you, so let's make sure. If it is a geometric sequence, I should multiply by 3/4 again, and I should get a shaded area of 27/64. And should you break this up into all its little triangles, and I'm not going to do that for all of them, or will I? You will see. I might as well finish at this point, shouldn't I? I screwed up. Oh well, there are 64 and there's 27 of them are shaded in. And so this is most definitely a geometric sequence, which means now this should be really quick. The hardest part's been done. Although I don't like how I drew that, so I'm just going to erase that and make it, there we go. But the hardest part's been done, which was seeing the pattern and realizing how I can now, if I want to find the total area of all the shaded regions, I just need to find the infinite sum, and which is always the area of the first term, which in this case is the area of 3/4, divided by 1 minus the common ratio, which is also 3/4, which is the same as 3/4 divided by 1/4, which is the same as 3/4 times 4/1, which is quite pleasant. It's just exactly 3. So 3 square units. And in general, once you see how a pattern connects to a geometric sequence, then this formula is quite pleasant. I mean, really, just to kind of wrap up, this right here, in my opinion, is kind of unique in that it is an incredibly simple formula in terms of how it looks, just first term divided by 1 minus the common ratio, that summarizes something really quite abstract, the idea of adding an infinite number of terms up and getting a finite number, a non-infinite number. But again, this only is appropriate if we actually have a term that each subsequent term gets closer to 0 if it's convergent. Otherwise, this formula is meaningless.